So this is where we left off in the previous video. We were talking about chromatography, and we used some fancy words to make us sound a little smarter. And this is stationary phase, mobile phase, and elution. And we started talking a little bit about method development as well. So now what we want to do is that we want to turn our focus, and we want to take a look at some of these words that we have just described. And the very first one that I want to target is this thing called the mobile phase. Now remember, the mobile phase is the liquid that does the pushing. Without that liquid, your components will not go through the column. Okay, with that said, there are tons of choices of mobile phase that's out there. And these choices really depend on what kind of separation you want. What kind of compounds are you looking for? Because those choices are very important as far as the mobile phase is concerned. So when I take a look at the mobile phase, there's going to be three common mobile phases that are out there. One of these is the horrible, dangerous killer known as water. Yeah, if you don't believe me, if you take a look at the safety data sheet for water, and that's what they're called now, safety data sheets, SDSs, no longer MSDS. They took the M off of it. If you look at the material safety data sheet or safety data sheet for water, it's going to say in large quantities it can kill. Well, you reckon? I guess it would. Anything probably in large quantities is going to kill. But water is one of the mobile phases that we can use for HPLC. Alright, so that's not fancy. The good news is that this is readily available. The good news is that this is fairly cheap. As long as we've got good quality water in the lab, then that's really all that we need. So when we say water, we're not really talking about tap water. We want to make sure that we all understand that this is deionized water or distilled water. We want this as clean as what we can get. And what we have in our lab at the ChemTech program on campus is a deionized system. So it's not distilled water that you'll be using, it's DI water that you'll be using. It takes all of the ions out of the water. So that's one of the mobile phase choices that we have. Another mobile phase choice that is very common to us is this compound that we abbreviate as MEOH. MEOH stands for methanol. That's the abbreviation that we use, and that's typically used in a laboratory all day long. So this is methanol. Methanol, if you look at the ending of OL, it is a alcohol. So at the ABC store, that alcohol, that's not methanol. That is something that we call ethanol instead, or ethyl alcohol. Okay, that's different. This is methanol. The structure for methanol, if you want it, because we gave it to you for water, if you want the structure for methanol, it is CH3OH. You can also write this together if you wish. It doesn't really matter. Sometimes I just like to showcase the important parts of the molecule, and I do that by drawing the bond, which is here, right? So there's the structure for methanol. Methanol was the compound that was making these moonshiners go blind. So up in the hills and up in the mountains, when they were making their moonshine from corn or whatever they were using to get different types of alcohol, they would distill the alcohol off. If they distilled the alcohol off, they wanted the ethanol to drink. But if they weren't careful, the methanol would come off as well. And it's the methanol that's the problem. The methanol causes people to go blind if you ingest it in large quantities. You've got to go to the hospital, and the way that they solve that is that they pump you full of ethanol. So they basically make you drunk. So a hospital situation, if you have methanol poisoning, is that they get you drunk with ethanol, so that way your alcohol dehydrogenase will use the ethanol because it's in larger amounts concentration-wise versus the scattered methanol that's still in your system. And then maybe the methanol can go through your system without getting processed as much. So that's how they treat alcohol poisoning if it's related to methanol. So that's your second mobile phase that's very common for HPLC analysis. Finally, the third common mobile phase is something that we call acetonitrile. And acetonitrile is an organic compound, and a nitrile group is a carbon with a triple bond N. That's the nitrile. Sometimes people call this cyano. And the word acete, A-C-E-T, in chemistry means two carbons. So acetonitrile is a two-carbon chain with a triple bond N at the end. Now this carbon's got to have some other stuff on it, right? So this has 3 hydrogens on it, CH3, C, triple bond N. That is acetonitrile. So these are the 3 mobile phases that we use for the piece of equipment. Sometimes, depending on the method, we use other things than these 3. But overall, these are the most common. The problem with acetonitrile, it's not really poisonous. We can handle it quite well. It's not really an issue as far as that's concerned. The problem with acetonitrile is that it's very expensive. A lot of times we order things based in milliliters or grams, and when we order acetonitrile, a 500 milliliter jug of acetonitrile can easily cost $700 to $1,000 per jug. And this machine drinks it like crazy. So that's an issue with acetonitrile runs. If you're using acetonitrile, it's going to be very expensive because acetonitrile is very expensive, and it might take quite a bit for your separation to take place. So that's the drawback with using an acetonitrile method. We have acetonitrile in the lab. We use acetonitrile ourselves for the labs that we have in our program. And you're more than welcome to use acetonitrile as well for your research project. So it is supported, but just keep in mind that more acetonitrile is more expensive method and more expensive to run as far as a research project is concerned. But we do have it and we do use it. Don't feel ashamed if you find something that requires it. It's okay. So this is the story with the mobile phases. Depending on what else, though, we can easily include buffers into the mobile phase as well. This is okay. So sometimes you will see a buffer integrated into the mobile phase composition. And these buffers could be a pH buffer of 4 or a pH buffer of 7, because maybe the compound that you want to study, maybe it has something acidic. So if the compounds or the components are acidic in nature or are basic in nature, they accept protons or they get rid of protons, then very often you are going to see a buffer being required in the mobile phase prep, because we don't want these compounds to kick off hydrogen or to gain hydrogen whenever they want. We want them to kind of be at equilibrium. We want them to be stable. So a buffer is sometimes required for that process. But there's others out there. It doesn't have to be limited to these 4. There are other mobile phase choices that we have that we can put on the machine and allow it to do its job. But these are the four, mainly three, that you're going to be seeing when you start looking at the project. Whatever topic that you pick maybe requires an HPLC run. You probably will see water or methanol or acetonitrile required. In our lab, through our instrumentation training, you will see water or acetonitrile or methanol being used for that purpose. But there are others. There are others. Just be prepared. Don't let it surprise you if you see it in any kind of chemical literature at all. All right, so that's the story with the mobile phase. The issue, though, is that these mobile phases are never really pure. We mix these mobile phases up. So that's typically what you will see in all of the methods. You will see a mixture of mobile phase. So for instance, it could say you need a 60-40 methanol and water mix. Okay, so what that means is that you need to make a mobile phase that's 60% methanol and 40% water. So if I'm making 100 milliliters, I would take 60 milliliters of methanol, 40 milliliters of water, and mix it together, and that is what I would run. If I'm making a liter, I do the same thing. 60% of 1 liter, that's 600 mils of methanol. 40% of a liter, that is 400 mils of water. And I would mix those two together, make a liter of solution, and go run it. Some of the instrumentation, though, will do it for us. That's the nice thing about the HPLC equipment, is that you type in, I want you to make a 60-40 mix of methanol and water, and it knows what to do. And it will mix it for you, and it will pump it into the machine for you. And our instrument does just that. You tell it what you need proportion-wise, and it will mix it on its own as it's needed, and it will send it into the piece of equipment. So this is something that you really do not have to worry with as far as our instrumentation is concerned. There's other instrumentation out there, though, that's something that you might have to do in the beginning, especially if it's an older piece of equipment that you run across. So now that we've talked about the mobile phase, let's turn our focus to the stationary phase of the column and the instrument now. So remember, stationary phase was just the solid stuff that went inside of our tunnel. The stationary phase is typically two choices here. One of this is silica, and the other choice is something that we call alumina. Okay, so these are our two main choices of stationary phase. No longer do we use calcium carbonate like Tisfiat did back in his day. We use something a little bit better. This tends to separate things a little bit better for us now that we've played around with it for a while. And silica and alumina are two of the most common things that are out there. Silica, if you want the structure for it, is SiO2, and alumina is Al2O3, also known as aluminum oxide. These two things are slightly different. Silica and alumina are similar, but they're different. And the reason that they're different is because they have different polarities. Okay, so over here to the side, I'm going to put polarity because this is very important in HPLC. It's something polar. And polar, if you don't know, is defined as a compound that has an unequal sharing of electrons. Okay, so for instance, if I had water, here's the Lewis structure of water. Water is a bent molecule, and water has electron pairs on the center atom, and it's bent. And there's an unequal sharing here. You want molecules, traditionally if you're looking for nonpolars, You want molecules that have taken those dots and completely spread them across the molecule itself. In the case of water, though, they're all clustered right there in the center. So this molecule is polar for that reason. I see dots here on the center. They're not equally shared. If I take a look at methanol, CH3OH, and I draw the Lewis dot structure for this thing. Okay, so here's carbon, and there's 3 hydrogens on that carbon, and there's another carbon, and here's an oxygen, and a hydrogen. Oh, sorry. I drew ethanol, not methanol. So let me go back and fix that. So here's O and H. And if I complete the Lewis dot structure, this is what methanol looks like. CH3, there's no dots on any of those. Oxygen, though, has 2 sets of dots and a hydrogen. Well, again, I see an unequal sharing of electrons throughout the molecule, right? It looks like all of my dots are here around the oxygen. None of them are over here on this side, right? None of them are over here. They're all clustered and they're unequal sharing. So this methanol, well, it's a polar molecule as well. Okay, well, if I look at silica and if I look at alumina, the same kind of concept exists here. These both are polar molecules. Silica and alumina are polar. So in a general science course, you often come across the statement that says like dissolves like. That means polars love to hang out with polars. And nonpolars love to hang out with nonpolars. So, if I make a column, and this column has SiO2 in it, which is silica, and I put a compound in that column, and if this compound is polar, that polar substance, like dissolves like, they have a natural attraction to each other, will hang out with the stationary phase a little bit longer than a nonpolar one. So this is where this video is going to stop, and we're going to pick up with this theory in the next one. We're going to expand this concept of polarity and why things separate the way that they do next. So stay tuned. I know that I've got you on a cliffhanger. Ha 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 ha.